Hey there, everybody. So in this video, we're going to be graphing linear inequalities. First off, let's revisit what this idea of a solution is. Okay, so a solution to an inequality, when I plug in these numbers, is going to make it true. So we get negative 2x plus y greater than or equal to 12. And the point that I'm trying to test is negative 3, 7. So remember, this is my x, this is my y. So I'm going to plug in negative 3 for x and 7 for y. And I'm going to see, is what I'm left with, is that true? All right, so negative 2 times negative 3 is 6. 6 plus 7 is 13. Is 13 greater than or equal to 12? Yes, it is. So is negative 3 a solution? Negative 3, 7 is a solution. Is negative 3, 7 a solution? And it is, because when I plug it in, it checks out. All right, what about the next one? So we got y is greater than 2/5 x plus 3. We're testing the point 5, 5. So I plug in 5 for y and 5 for x. And now I need to simplify and see if it's true. Is this true? That's what we're trying to find out. So we get 5 is greater than 2/5 times 5. Well, the 5s are going to cancel out there. Just leave me with 2. 2 plus 3 is 5, so 5 greater than 5. Is 5 greater than 5? No. No, 5 is not greater than 5. 5 equals 5, but I don't have equality as part of this inequality symbol. I just have greater than. So no, 5, 5 is not a solution. All right, and the reason we're talking about solutions is because these are the different types of graphs we could have for inequalities. All right, now if you recognize the boundary line of each of these is y equals 2x minus 3. It's the same exact boundary line in slope-intercept form. All right, but the graphs, the shading of it looks completely different. Now, why is there shading? Why isn't there just a line? Remember, this is an inequality symbol. All right, so it's not saying y equals 2x minus 3. I'm not restricted to just what's on the line. All right, in this case, in the first one, in this red, it says y is less than 2x minus 3. And so that means anything that's less than 2x minus 3 will satisfy this inequality. All right, so like the solutions that we were talking about up here, this is a solution, this is a solution, this is a solution, this is a solution. Anything that falls in that solution region is a solution. All right, so if you have a case like y is less than 2x minus 3, we don't have equality, so notice that the boundary line, this is called the boundary line, and this whole part is called the solution region. All right, so if we have y is less than 2x minus 3, notice that the boundary line is dashed. Why might it be dashed and not solid? All right, well, we don't have equality here. All right, so it's a dashed line because it's just setting the boundary. All right, it's dashed because nothing on that line works. Just like up here, 5, 5 is on that line if I were to graph it as a solid line. All right, but it's not a solution to the inequality. So the dashed line here represents that anything that falls on that line is not included. Okay, same thing with y is greater than 2x minus 3, this green one. It's a dashed line, but notice how, since it's greater than, we shade above. We shade above the line. Okay, and then in the other two, we have y is less than or equal to 2x minus 3. So this looks very similar to the red one. We shade below, but the boundary line is solid because we have equality here, less than or equal to. That means anything that falls on the line as well as in the solution region is a solution. Okay, same thing down here. Y is greater than or equal to 2x minus 3. I still shade above, but anything that falls on the boundary line is also going to be a solution. It's also going to be included because I have equality here. Okay, so graphing works very similarly to how we did it when we were dealing with linear equations. All right, we got to solve the inequality for y, which it's just like getting into slope intercept form. So y, and then instead of an equal sign, we're going to have some inequality symbol, mx plus b. Okay, just the new thing, remember, when we're dealing with inequalities, if you multiply or divide by a negative, you got to flip the inequality symbol. All right, and then that is going to be our boundary line. And we graph that just like we would. We start at the b value, which is our y-intercept, and then we apply the slope, which is the m value, rise over run. It's a solid line if we have equality, so less than or equal to or greater than or equal to. All right, and a dashed line if it's less than or greater than, if we don't have equality there. Okay, then we can either test a point to determine which way to shade, or we can remember that if it's greater than or equal to, we shade above the line. If it's less than or equal to, we shade below the line. All right, it's very similar to like if we had a number line, then if it was less than, we would shade below, and if it was greater than, we would shade above. All right, so it works very similarly to that, but instead of just a number line, we've got two variables here, an x and a y. So we've got a coordinate plane. We got a two-dimensional thing. Okay, so let's go through these. Let's graph. Graph the linear inequalities and find their solution regions. So we get y is less than 3x minus 7. This is already in slope-intercept form. So this is my b value. That's where I'm going to start at -7. And then this is my slope, which is m equals 3. So we could say 3 over 1, rise over run. Or we could say -3 over -1, rise over run. So starting at -7, I'm going to go up 3 to the right 1. Up 3 to the right 1, up 3 to the right 1. Or I could go down 3 to the left 1. Okay, I'm just going to get another point here. And then, now we can graph it. Now be careful, we don't want to just connect the dots, graph a line. All right, since its y is less than 3x minus 7, I do not have equality, therefore it's going to be a dashed line connecting these points. Still put my arrows on it. All right, so y is less than 3x minus 7. And because it's less than, I'm going to shade below the line. I'm going to shade below the line. So if I get out this, anything that's in the shaded region is going to be a solution. All right, so this is my solution region. Sometimes you might see us put a capital R there just to say that's my solution region. So anything that falls on that in that shaded region is going to satisfy this inequality. Nothing on the boundary line works because I don't have equality, and nothing over here works either because it's not in the shaded region. Okay, so that's how these differ a little bit from just graphing straight up linear equations. Okay, so going down, just determining whether points are solutions. So 3, 2. So if I graph 3, 2, if you notice, that's on the boundary line, which means no, it's not a solution because it's on the dashed boundary line. Okay, what about 5, -8? Well, 5, -8 is right there. That's definitely a solution. Yes, it's in the shaded region. And then last but not least, negative 5, 4. That's not a solution because it's not in the shaded region. All right, it's outside the boundary line. It's on the completely other side of this coordinate plane. All right, so that's how you can determine whether or not you have a solution once you have the graph. Okay, we could also take those numbers and plug it into the inequality and see if what we're left with is a true statement. That's what we started this video by doing. Okay, so that's also a possibility. All right, what about the next one? Notice, x minus 2y is greater than or equal to negative 6. This is not in slope-intercept form. So we got to do a couple things to get into slope-intercept form, which means we got to solve for the y. We got to get the y by itself. So first thing I'm going to do is subtract the x from both sides. So I get negative 2y greater than or equal to negative x minus 6. Then I have to divide everything by negative 2. So I'll get y, and then this is where we got to be careful because we divided by a negative. So I have to remember to flip the inequality symbol. Flip the inequality symbol. So then continuing on, we've got negative 1 divided by negative 2, which is going to give me positive 1/2 for my slope. So we get 1/2 x, and then negative 6 divided by negative 2, which is positive 3. So now we are ready to graph. So this is my y-intercept. So I'm going to start at 3. This is my slope. So 1 over 2, this is going to be my rise over run. So I'm going to go up 1 to the right 2, 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 or I could go down 1 to the left 2. That's following the same pattern. All right, so we got our lines, or we got our points there. Now, to connect it, we've got less than or equal to, which means that it's going to be a solid line connecting these. So we've got a solid line, put my arrows on the end, and if y is less than or equal to, that means we're going to shade below the line. Because it's less than, we're going to shade below. So I got this, and I just start shading this in. And this right here is going to be the solution region. All right, so anything on the boundary line, since I have equality, or anything below the boundary line will satisfy this inequality. So let's check, are these points? So we've got, first off, we've got 0, 7. That's way up here. No, that's not in the shaded region or on the solid boundary. What about 6, negative 5? Well, that's clearly in this shaded region, so yes, in the shaded region. And then negative 2, 2, oops, erased it, it's right back. Negative 2, 2, that's on the boundary line, but since I have equality, since it's a solid line, I do include it. So yes, it's on the solid boundary. Okay, so there are a couple examples on how to graph linear inequalities. All right, in the next video, because this one's probably going a little bit long, in the next video we'll talk about how to write linear inequalities if I give you the graph. All right, so make sure to tune into that next video.